Welcome to geometry. We want to take a look at section 16 today, triangles in Euclidean geometry. So as a result from the previous section, we can begin to work in with triangles and come up with some results about triangles. In particular, the angle or the measure of the angles of a triangle, right? Measure of the interior angles. Their sum is 180 degrees. So in particular, sum of the measures of the interior angles of a triangle is 180 degrees. All right, so let's take a look at the proof of this, and it is quite short. So what we're going to do is we're going to use a line that is parallel to help us out here. Call these angles 1, 2, and 3. All right, so the first thing is what we're given. Well, we're given triangle ABC. So we have a triangle. Excellent. The next thing is let's let this line L be a parallel, a line that is parallel to BC that passes through A, which is unique. So let L be parallel to BC through A. And we have that because of the Euclidean parallel postulate. I suppose we have that it's unique because of the Euclidean parallel postulate. There is one, and it is unique. Excellent. So we know that the measure of angles 1, 2, and 3 is 180 degrees. If we were to consider, there's technically two different things going on here. Right? If we were to take the angle 3 and this larger angle by the supplementary angle postulate, their measure would be the sum of their measures would be 180 degrees. But this larger angle is given by, or the measure is given by the measure of angle 1 plus the measure of angle 2. So overall, we get the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 is equal to 180 degrees, and we just call it by the supplementary postulate. Excellent. But the previous section gave us that angles 1 and angle B are equal to each other. Angle 1 is equal to angle B, because when we have parallel lines, then the alternating interior angles are congruent. So we'll call it congruent there. And angle 3 is congruent to angle C. Actually, you know what? Why don't we back this up and use measures here? Because we really want to use some substitutions in this equation. So let's say the measure of angle 1 is equal to the measure of angle B, and that the measure of angle 3 is equal to the measure of angle C. Right? 1 in B, 3 in C. And this is by the converse of the alternate interior angles theorem. But we can substitute these into equation, or into line 3, to get that the measure of angle B plus the measure of angle 2 plus the measure of angle C is 180 degrees, which is exactly what we were trying to show. And that's by the substitution for A and for B into line 3. Excellent. So this is very nice formal proof of what's going on. If you were a little unsure, if you needed a little bit more convincing, right? 3 and C are supposed to be the same, 1 and B are supposed to be the same. So what you could do is you could just take a sheet of paper with a triangle, take a sheet of paper, cut out a triangle. It's a pretty terrible triangle here. And rip off the 3 corners and line them up to notice that when you put them together, what you get, right? Let's try this again here. What you get, the 3 pieces of torn paper, when you put the points all together, you get a flat line here. And that's what we're trying to say, right? The sum of the 3 angles is 180 degrees, so you end up with a straight line. All right, in that case, using that, we could show that the measure of each angle in an equilateral triangle is 60 degrees. But I'll leave it to you to piece together why exactly this theorem gives us that each angle is 60 degrees in an equilateral triangle. Excellent. Now, the exterior angle equality. Exterior angle equality. The measure of an exterior angle of a triangle, so if we have a triangle with exterior angle, this exterior angle is equal to the sum of the non-adjacent interior angles. The sum of the measures of the non-adjacent interior angles. Excellent. So this theorem would imply the exterior angle inequality, right? So we have here that the sum of the exterior angle is equal to the sum of the measures of the interior angles that are non-adjacent. So if we were to subtract one of those away from that side, then of course this is larger than that, right? The exterior angle inequality says that the exterior angle is larger than the non-adjacent interior angles. So we want to be careful about what we're citing here. Notice the difference in names. This is the exterior angle equality, whereas the other is the exterior angle theorem. So this is exterior angle equality. When we want equality, we get this. When we want an inequality, we use the exterior angle theorem. But that's all that we want to take a look at for now. We'll return shortly to see the remaining portion of section 16.